Okay, so welcome to the 6th session on convex optimization. So we are happy here to have Zai Chen, who is going to talk about SADA-GRAD, strongly adaptive stochastic gradient method.
Thanks for the introduction. I'm from University of Science and Technology of China. It's my honor to introduce our work. This is a joint work with Yixu, En Hongchen, and Tian Baoyang, and was done when I was in Professor Yang's group in University of Iowa. This is the outline of this presentation. First, we will go through the introduction and background. What we are trying to solve is a stochastic convex optimization problem. The definition, the problem setting is as follows. Here we are trying to minimize the convex objective function capital F, and the feasible domain omega is a closed convex compact set. Both capital F and F are proper or semi-continuous convex functions with respect to W. And here Here the psi is a random variable subject to some probably unknown distribution P. And to solve this problem, we assume that we can access the stochastic subgradient from a stochastic first-order oracle in each iteration, and we assume that the infinity norm of stochastic subgradient is no greater than some constant gamma. There are many applications in machine learning can be viewed as solving a convex optimization, stochastic convex optimization problem. A famous example is the convex risk minimization problem in supervised learning. Here, W comes from a hypothesis class H, and the randomness comes from the sample data label pair from some known distribution D. And the fundamental problem in optimization is the iteration complexity. It is the number of stochastic first-order oracle needed to find an epsilon approximate solution such that the expectation of optimality gap no greater than some small constant epsilon. Here W star is one of the global optimal solution, and this definition can be described by this figure. One of the most famous algorithms in recent years is ADA-GRAD, and the basic idea of ADA-GRAD is to choose a step size that's adaptive to each feature based on the learning history. The whole algorithm is described in the following block. And to adaptively choose a step size, it has to maintain this intermediate variable STI for ith coordinate in all iterations. And in ADA-GRAD, it gives an adaptive bound such that in the numerator it's actually the summation of STI for all with respect to all dimensions, and in the worst case, STI grows in the order of square root t, which give us an iteration complexity of 1 over epsilon square in the worst case. But it actually performs better in practice because if the stochastic subgradient is sparse, then the numerator will grow slower than square root t. Then the convergence rate will be faster. And in our paper, we consider the strongly convexity assumption. Here is the definition of strongly convex function, and lambda greater than 0 is a strong convexity modulus. ADA-GRAD can solve the stochastic SEO problem with under strong convexity. The only difference is that it has to choose. It has to change STI to be ST square here, which is in red, and it returns average solution, just like in general stochastic convex optimization situation. And there are also many variants of ADA-grad in strong convex scenario, and all this method give an adaptive bound to be like this. And here in the denominator, here in the numerator, it is the sum of a log STI square, and it's defined to be like this. So in under strongly convexity assumption, this term actually grows in the order of t. So in worst case, it's give an iteration complexity of log t over lambda t in the worst case. And in this case, if the stochastic subgradient is sparse, we can see that it's only give a better constant. So as a result, SADA-grad and its variance under strong convexity assumption only could benefit very little from sparse stochastic subgradients. So this is the motivation of our paper. And in our paper, we propose the new variant named SADA-grad, and it achieved the optimal convergence rate under strong convexity assumption in worst case, and it could enjoy greater benefits from sparse stochastic subgradients. And in our paper, we also propose two variants. The first one is to reduce the effect of non-stochastic regularization term on the iteration complexity, and second one is to handle the issue that if in the implementation that the strongly convex parameter lambda is unknown. Here we'll face the assumption. We assume that the objective function capital F is finite valued, and the starting point has an optimality gap no greater than some constant epsilon 0. And in our paper, we used a weak strongly convexity condition. It's described in equation 3, and it's also known as second-order growth condition in other paper, which is weaker than strongly convexity. Our SADA-grad is built upon ADA-grad. It's called ADA-grad stage by stage, and initialize the ADA-grad in the current stage by the return solution from previous stage. And we also maintain two variables in each stage. The first one is eta k here. It's actually control the initial step size in the current stage. And the second one is eta k. It's actually the desired optimality gap in the current stage. In the inner loop, we called original ADA-grad. It's completely the same as original ADA-grad in the blue. And the main difference is the stop criterion. It's described by formulation 4. On the right-hand side of, on the right-hand side of this inequality, we can see that it's related to STI. We can see in this line, we can see that STI is related to the stochastic subgradient, which means the stop criterion in each call of ADA-grad will change in every iteration, may change in every iteration, and it returns an average solution in the current stage. Well, the proved theory is some kind of difficult to understand. I can summarize it in brief. If certain assumptions are held, we can our algorithm will give will returns an epsilon approximate solution after capital K calls of ADA-grad, and in each call the stop criterion is described like this. The next is iteration complexity. The iteration complexity of ADA-grad is d gamma square over lambda epsilon, which is inverse case, and since this stop criterion is adaptive to the data, and we can give a better convergence rate if the stochastic subgradient is sparse. For example, here, if STI intermediate variable STI grows on the order of in the order of t to the power of alpha, and alpha is less than 1/2, then following the stop criterion, we can Following the stop criterion, we can see that the total iteration complexity will be like this, and the exponential will be less than 1, which give us a faster convergence rate than 1 over lambda epsilon. And the second example comes from the original undergrad paper. If i's coordinate appear with probability pi, it's defined like this, then we have that the total iteration the dependence of total iteration number will be put into this log term, the square log term, which means it will get a better dependence on the dimensionality in this case. So actually, in practice, most of machine learning applications has a non-stochastic regularization term. It's phi w here. And as we presented in the previous slides, we can see that the adaptive the adaptive convergence rate is related to this STI. It's actually the L2 norm in the i's coordinate for all iterations. So if we can reduce this STI, we can get a better dependence on the stochastic subgradients. So we proposed proximal variance. From now on, we let GW refer to the stochastic subgradient with respect to small f. This is a randomness construct, and we denote the upper bound of this subgradient L2 norm of subgradient of small f by capital G, and we kept the outer loop unchanged and defined this AK in case stage for convenience. In the inner loop, and we solve this proximal mapping stage by stage, which is some kind of similar in our original undergrad paper, and the stop criterion is changed to be like this, and there are some issues happen here if we introduce the proximal mapping. So we, unlike original undergrad paper, we solved it by taking average from the second to the tk plus 1 iterations as a return solution. So by doing this, we can get a similar dependence on a similar convergence rate with the dependence on the stochastic subgradient, just like original undergrad, and here STI will no longer has any. Okay, thank you. Will have no longer have any relation to the non-stochastic term. Another variant is that in practice, the strongly convexity parameter lambda may be unknown or underestimated. So we solve this by give a restart strategy. It's called Salagrad stage by stage, and give an initial guess of this strong convexity parameter greater than true lambda. And we prove that it can give a similar convergence rate, just like we know the true strongly convex parameter. We also testified proposed algorithm in two machine learning applications. The first one is smooth hinge loss plus L1 norm regularization, and zeta here is a control parameter. Smooth hinge loss is defined like this. The second one is classical hinge loss SVM. And actually, C here controls the sparsity of stochastic subgradients, and lambda is actually the lower bound of strongly convexity. Here is a part of experimental results from RCU1 dataset, and the red line is our experimental results. It performs comparable or even better than existing baselines. So, in conclusion, we proposed a variant of ADA-grad named SADA-grad, and it achieved optimal convergence rate with respect to epsilon. For stochastic strongly convex optimization problem, and it enjoys better dependence on sparse stochastic subgradients, and also we propose some variants to make it better in practice, and we also provide applications in machine learning applications to testify the correctness of our proposed theories and algorithms. So thank you for paying attention to our work. Our poster will be in hobby number 3. Now it's my honor to answer your questions. Thank you.
Okay, so we have time for a few questions. And so while we answer the questions, please also the next speaker come to prepare his laptop. So, yes, since I have the microphone, you will have to come here.
Hi. Yeah, thanks for the talk. So, Mike, you in the title seems to imply that the algorithm is adaptive to strong convexity. If the strong convexity is changing, can you adapt to that too? I didn't figure that out. I couldn't figure that out from your slides. That means at some part it's more strongly convex, and the other part it's not that strongly convex.
Thank you for the valuable question. Actually, this is some kind of more complicated scenario. If the objective function is piecewise quadratic, actually no, we cannot handle this problem. But actually, if in the convergent trajectory, the strongly convex parameter goes smaller than in this scenario, I think our algorithm could handle. So for other more complicated scenario, it cannot be handled by our algorithm. Thank you.
Any another question? So I have one which is very naively. So you have a proximal variant. So to minimize the sum of f of x plus phi of x, where phi is the regularization function.
Yeah.
So if you have, let's say, logistic regression model with strongly convex regularization, would you use the proximal variant, where phi is the squared L2 norm, or simply use the variant that puts the regularization inside f?
I think in the theory, if we handle it via proximal mapping, it will give better dependence on the stochastic subgradient, but maybe it will bring more complexity in each iteration. So it depends on the true situations. Thank you.
Okay, thank you. So any questions? So if not, we can thank our speaker again. And so we are pleased now to welcome Tianbao Yang, who is going to present his work about level set method for convex optimization with finite sum constraints.
Thank you for the introduction. Hello, everybody. So I'm going to talk about a completely different problem, okay? So in different setting. So this is joint work with my colleague, Qihang Lin, and the student Renchao Ma. This is the level set method for convex optimization with finite sum constraints. Okay, so we consider convex optimization problem in this form. We minimize f0x function, satisfy a bunch of functional constraints fix minus ri is less equal than 0. Okay, Here, let f star denote the optimal objective value. So here we make a few structural assumptions, which are actually popular in machine learning. So first, each fi, including the objective function constraints, is written as a finite sum form, which is the average of some. You can consider the phi is like loss function, okay? C is like the data. You consider the x is like the model in machine learning, okay? So basically, each fi is like the sum of the loss on the training data. Okay, and here we assume all the involved functions are convex, all right? So this is the problem. So this problem has some applications in machine learning. So for example, Newman-Pearson classification, where you want to minimize the false negative rate, so which is the loss on the positive data. And at the same time, you want to control the false positive rate, so which is the loss on the negative data set. Okay, so this is a perfect example failing in our framework. So another example is fail classification with fail constraints. Although the original problem with fail constraint could be non-convex, but you can actually use some convex relaxation method to convert the problem into maybe a sequence of constraint problems with functional constraints like the problem we consider in this paper. Okay, just give you some examples. Okay, so this problem is actually very challenging. So in machine learning and also many optimization studies, okay, so gradient, sub-gradient methods need to perform projections at every iteration, right? Frank-Wolf method is another class popular method which needs to perform linear optimization of the constraint domain, okay? But if you have a bunch of a number of constraints, functional constraints, right, either projection or linear optimization over the constraint domain could be very expensive. All right, so that's what we want to avoid. Okay, and there are also a long list of other algorithms for constraint problems, which I cannot list here, but most of them cannot guarantee feasibility. Okay, so in this paper, our main contribution, we propose a stochastic algorithm which can achieve feasible and also epsilon optimal solution with 1 over epsilon square stochastic gradient complexity. And most importantly, we don't need to perform any projections or linear optimization over those functional constraints domain. Okay? But also we need some conditions. So our condition is that first, we assume there exists a solution X bar which is strictly feasible, which means all the constraints are strictly satisfied. Second, we assume that the proximal mapping of the conjugate of the loss function, phi, can be efficiently computed. Unfortunately, for many loss functions in machine learning, like square loss, hinging loss, squared hinging loss, okay, so the proximal mapping of the phi star can be efficiently computed. All right, so this is the main contribution here. Okay, so let's talk about our method. So it's based on level set method. So we first define a level set function, HR. So basically, we move all the constraint functions, fix minus ri, into this objective here. We take a max. f0x objective minus r is a level parameter, okay? We take a max of this and minimize over x, okay? So this is this optimal value give us hr, okay? Which is a level function depend on level parameter r, okay? Level parameter r. Okay, so this is a min-max problem. We actually write this max as this term here, this max here, by introduce the dual variable y, which is in a simplex, okay? hr. Okay, so a nice thing about this level function is that, okay, previously these studies have shown that HR is a decreasing function and convex in R. Okay, and convex. And most importantly, when R equal to F star, the optimal objective value, that gives HR equal to 0. So H at F star is equal to 0. Okay, so this means that we can change the original problem to minimize original problem to finding the unique root of HR. Okay, if I find the unique root of HR, I can approximately solve the original problem. So that's the idea. Okay, so think about right now you have you reduce the problem to this root finding problem. Okay, so if you can evaluate HR function exactly, you can take any procedure you want, for example, binary search to search the root of HR, right? But most challenging is that HR cannot be computed exactly. Okay, so we want to address this issue here. Okay, so this is the general framework here. So we need to we generate a sequence of the R values, the level values. Okay, so we let this sequence convert to F star based on root founding scheme, and in order to update RK, okay, because we don't know HR, in order to compute RK, we need to have some oracle. Okay, so here we assume the algorithm A, which is given input R and our parameter theta, can return 3 values, LR, UR, and SR, and a solution X bar, such that the 3 conditions satisfied. So first, LR is the low bound HR, UR is the upper bound of HR, okay, and in particular, UR is the max of Fi X bar minus Ri. Okay, so the first condition. Second condition saying that the low bound HR is actually not very bad. Okay, so you want is a close approximation of HR. So third condition is actually so-called a minor range condition. So we want LR and S. We can use LR and SR to construct the linear function. Okay, linear function in terms of R prime, which is the low bound of HR prime. Okay, so I will tell you why we need this condition. So that's why we call this method called affine minorized feasible level set method. Okay, so basically you can start from a feasible solution, which is give you a R0, pick a R0. Okay, and every iteration, so you compute upper bound and lower bound of the HR function, and then because they are good approximation of HR, so those are negative values. Okay, and then we update R like this. We add this UR to this current value to generate a new value. Okay, because UR is negative, so we guarantee R is always larger than F star. It's always larger than F star, and also is approaching to the F star. It's approaching to the F star. Okay, so the second idea is how we can terminate this procedure, right? How can we terminate the procedure? So one criterion is if the R value, the level value is close to F star, less than epsilon, we can terminate. And we can find a solution which is feasible and epsilon optimal. Okay, let me tell you why. So if I store when this happens, okay, so recall that our algorithm A, the oracle, can return a solution xk such that urk is less equal than 0. Okay, so when this happens, so which means all the constraints here are feasible. And also, this one is less than 0 because RK less than F star plus epsilon, so we have F0 XK less than F star plus epsilon. So which means XK is feasible and epsilon optimal. Okay, but the question is how can we detect the distance from RK to F star is less than epsilon? So that's why we need this the minor and the lower bounds. Okay, because we can use L and S to construct a linear function at any R. So for this linear function, we can compute the root such that this is equal to 0, and then the distance from R to this root is actually upper bound of RK minus F star. And this distance can be computed by L divided by S. That is returned by the oracle. So we can use this to determine when we can stop the procedure. Okay, so this is the final method. So every iteration, we construct low bound, upper bound, and S. If this happens, return, otherwise update R. Complexity, so we only need log number of iterations to update R, and complexity is dominated by the complexities of solving the min-max problem for constructing the oracle, okay? So I will summarize later. So the key here is to solve the min-max problem HR. So here we transfer the HR function into a min-max problem like this. We introduce another dual variable by using the conjugate of phi function. So this is actually a perspective function, which is also convex. So in this way, we can efficiently compute the upper bounds, lower bounds, and this S primary value in time linear to the data sets. Okay, and you can also use a bunch of algorithms, the primal dual algorithm, Mirror-Brooks, primal dual gradients, SVRG, to solve the min-max problem. Okay, and here summarize the iteration complexity. So compared to the previous algorithm, we can guarantee feasible, and also our time complexity is a list for different oracles. So if you have any question, you can come to our poster tonight. Thank you.
Okay, so we have time for one very short question, and in the meantime, could the next speaker come to the stage? Okay, so if there is no other question, let us thank the speaker again. I think you can just close it. Should work. Okay, so our next speaker is Clarice Poon, and she's going to talk about local convergence properties of Saga, ProxSVRG, and acceleration.
Hey, thank you for the introduction. This is joint work with Jingwei Liang and Carola Schoenlib. So I want to begin with an example. Let's consider the minimization of this functional. We've got a quadratic term and a regularizer. And you can think of the regularizer as, say, the L1 norm or nuclear norm. Now, in the last decade, there's been a huge amount of research which tells us that the L1 norm promotes sparse solutions and the nuclear norm promotes low-rank solutions. And when we're facing a problem like this, we've got a smooth term and a non-smooth term. A very basic way of dealing with this is the proximal gradient descent algorithm. And we know that the objective converges at the weight O1 over K, and we've got linear convergence on the strong convexity. But we may ask the question, what can we say about the structural properties of these iterates xk? And this is a typical observation. So on your left here, I'm showing you the convergence of the iterates in red in the L1 case, and in black, I'm showing you the support of the iterates. And this is a similar picture in the case of the nuclear norm, where the black now shows the rank of your matrix. So what you see is that initially convergence is quite slow, and at some point you identify your solution manifold, so the sparsity or your rank. And after that, convergence is linear, is much faster. And this is now fairly well understood in the deterministic setting where you do full gradient evaluations in this work. And under certain assumptions, it's been shown that after a finite number of iterations, you identify the solution manifold, and after that, you will have linear convergence. And the purpose of our work is to establish these properties in the case of variance-reducing stochastic proximal gradient descent methods. So in this talk, we'll be considering this problem. We've got the finite sum problem, we've got the regularizer R, and M functions on the standard convexity assumption. So R is proper closed convex. We've got M functions, these little fi's. They're convex differentiable with L Lipschitz gradient, and we assume the set of minimizers is non-empty. Now, we can really see stochastic gradient descent as a kind of inexact proximal gradient scheme, where at each step you introduce this stochastic error epsilon k. So for SGD, it is of this simple form, where these IKs are randomly chosen indexes. And now, since we're considering the finite sum problem, there's been a huge amount of work in the last few years which show that you can exploit past gradient evaluations to get much faster convergence rates. And so one such example is Saga, where you make use of M stored gradients. And another example is SVRG, where you do one full gradient evaluation and then reuse it for a set number of iterations. So the key remark that I want to make here is that the latter two are called variance-reducing methods, and unlike SGD, it's been proved by these authors that the variance of this error goes to 0 as k goes to infinity, and therefore they retain a lot of the nice convergence properties of full gradient descent, such as linear convergence on the strong convexity. And what we establish in our work here is that they also retain properties of manifold identification and local acceleration properties. So the key assumption on the regularizers that we'll make in order to have this identification is partial smoothness. So and this is due to Lewis from 2003. So we say that a function R is partly smooth at a point x relative to the set M if we have got three properties. The first is that restricted to the set M, you are C2 smooth. The second is that the tangent space is perpendicular to the space which is parallel to the subdifferential x. And the third is that as a set value function, you are continuous along the set M. So on a very high level, what this means is that as I move along this set M, I'm smooth, but if I move in the orthogonal direction, then the function changes sharply. So just to visualize this a bit, here I'm showing you the landscape of lasso. And what you see is the solution lies on this dotted ridge here. And clearly the function is smooth as I move along the ridge, but it changes sharply as I move in the orthogonal direction. So partially smooth functions are interesting because they encapsulate a lot of the commonly used regularizers, such as L1, nuclear norm, L12, L infinity, total variation, and so on. So in the case of L1, you are partly smooth at the point x relative to this set, which are all the vectors with support contained inside the support of x. And for nuclear norm, you are partly smooth with respect to the set of all matrices with the same rank as x. Okay, so how do we use this to establish identification and local acceleration? So roughly the theoretical framework in our paper goes like this. So first, we need to establish that the objective function sequence and this error all converge to 0 with probability 1 and not just an expectation. Then, under some non-degeneracy condition and partial smoothness, this automatically implies that you identify the manifold that you're partially smooth with respect to within a finite number of iterations. And once you identify your manifold, if restricted to this manifold, you have a local quadratic growth, then this gives us local linear convergence. So I just mentioned at this point that there's been the first work on manifold identification in the stochastic setting was by Lee and Wright in 2012. And they looked at this in the case of for the regularized dual averaging scheme. But the difference here is that because we're really looking at the finite sum structures, therefore we've got linear convergence. Okay, so specialized to Saga and S3RG, on the appropriate step size, we can certainly prove global convergence with probability 1. Then under this non-degeneracy condition and partial smoothness, this implies identification of a solution manifold within a finite number of iterations. Note that this is the standard optimality condition, except we need that 0 lies in the relative interior of this set. And finally, if restricted to this manifold, we've got quadratic growth, then this automatically gives us local linear convergence. Okay, so the key take-home message here is that globally you may be non-smooth, and perhaps you don't have strong convexity. But within a finite number of iterations, if you have partial smoothness, then it means that you identify a manifold that you are partially smooth with respect to, and you can really exploit properties of this manifold to get faster convergence. So here is just a numerical example where I'm showing you the support of the iterates for Saga and SVRG, and in the case of sparse logistic regression. And here is so you see that after identification, you have a linear convergence of the sequence. Okay, so the key point is that at some point you identify a manifold that is really could be of very low complexity, and there are some consequences of this in terms of acceleration. The first is that in certain cases, because of this low complexity, it means that at each iteration you may have lower computational cost in evaluating the gradients. So such is the case for L1 norm, since all your iterates will be sparse after a certain point, you can reduce the computational complexity at each iteration. And secondly, restricted to your manifold, you may have a much better Lipschitz constant. And this means that you can actually take a larger step size. So this is an example with lasso, where after identification, restricted to the manifold, you actually have a much better Lipschitz constant, therefore we can change the step size to obtain faster convergence. And a final two comments is that if your regularizer is locally polyhedral, such as in the L1 case or L infinity case, then there is actually a closed form solution. So provided your manifold is of sufficiently low dimension, you can actually have termination in finite time. And of course, once you identify the manifold, there is no reason to stick with proximal gradient descent. You could switch to different methods, such as higher order methods or conjugate gradient, which really make use of this manifold structure. So thank you for your attention, and we can find some code on this GitHub website.
Same, we have time for questions, and then if the next speaker could come.
I have a question that might be a stupid one, but so you showed this really interesting graph where you were switching to a larger Lipschitz constant once you had identified the support. Right. In practice, how do you know you identified the support?
So I didn't mention this, but actually we don't have any bound on the number of iterations before you identify the support, and this of course depends on properties of the regularizers. So in practice, you would just set some heuristics such as the manifold doesn't change within a set number of iterations.
Okay, so let us thank the speaker again. Okay, so the next speaker is Pan Xu from UCLA, and he's going to talk about continuous and discrete time-accelerated stochastic mirror descent for strongly convex functions.
Okay, thanks for the introduction. Welcome to my talk. I'm Pan Xu from UCLA, and this is joint work with my collaborator Tianhao Wang from Yale and my advisor Quanquan Gu. In this work, we propose a new understanding of accelerated stochastic mirror descent from a perspective of continuous time stochastic differential equations. Let me first remind you of the stochastic mirror descent. We aim to solve a constrained optimization problem, and where the object function is strongly convex and the variable x lies in a subset of the whole space Rd. And the stochastic mirror descent algorithm takes the following update, and let me illustrate it in this picture. We start with a point in the primal space and map it into the dual space using Laplace H. Here, H is a distant generating function of this set X. And in the dual space, we perform one step of stochastic gradient descent. Here, eta is the step size, and the g is a stochastic gradient. Then, we map the result back to the primal space using Laplace H star. Here, H star is a conjugate function of H, and the Laplace H star is often called the mirror map. SMD enjoys a convergence rate like follows, and in order to improve the convergence rate, accelerated stochastic mirror descent was proposed. The major difference here is the additional sequence generated by the linear combination term. This accelerated algorithm enjoys a convergence rate of 1 over k squared plus sigma squared divided by mu times k. Can we design new discrete time algorithms that match this optimal convergence rate? The answer is yes, and I will show you by discretizing stochastic differential equations. In this work, we propose a stochastic differential equation to characterize the accelerated stochastic mirror descent. Here, T is the continuous time index. Delta and beta are scaling parameters, and the BT is a standard d-dimensional Brownian motion. The first two terms here are called the draft term of the SDE, and the Brownian motion term is called the diffusion term. This is the first SDE that is proposed to characterize the accelerated stochastic mirror descent for strongly convex object functions. We prove that the solution xt of this SDE will converge to the minimizer x star. And in this convergence rate here, q is a constant such that the diffusion term is bounded by t to the power of q. And when q equal to 0, that means the diffusion term is uniformly bounded by constant. And this rate will turns to 1 over t squared plus 1 over t. And just to remind you, this exactly corresponds to the optimal rate of the discrete time algorithm ASMD. Now we have proved the convergence of the SDE, then we can design new algorithms by discretizing this. First, to discretize the continuous time SDE, we will treat each tiny time step delta as different discrete index. Then xt corresponds to xk, and xt plus delta just corresponds to xk plus 1. And similarly, we can discretize the continuous index of y. And now we need to approximate the time derivatives of x and y. In particular, based on the direction of derivatives, we have two different discretization schemes. The first one is called the forward unit discretization, where we approximate the time derivative of xt dot by xk plus 1 minus xk divided by delta. And alternatively, we can also replace the time derivatives of x by xk minus xk minus 1 divided by delta. And this is called the backward unit discretization. These two schemes has no difference in the continuous setting, but it will lead to different discrete time algorithms and totally different properties. Okay, then the first discrete time algorithm we designed is directly using the backward unit discretization scheme to discrete the time derivative of x and y here. And we got the optimal condition for this algorithm here. We proved that this algorithm can achieve the optimal convergence rate of ASMD. But however, as you can see from this optimal condition, in the first equation, we update yk plus 1 based on yk and xk plus 1. And in the second equation, we update xk plus 1 based on yk plus 1 and xk. Therefore, this is actually not an implementable algorithm. So that's why it's called implicitly. So to obtain a practical algorithm, we then propose to combine the forward and the backward unit discretization schemes. As you can see here, we update xk plus 1 based on yk and xk, then we update yk plus 1 based on yk and xk, and xk plus 1. So this is implementable, however, the convergence rate is not optimal in the sense that when sigma equal to 0, the dominant term will not change. It's still 1 over k. So to address the previous issues, we finally propose an ASMD3 algorithm here, which combines the forward and the backward unit discretization schemes, and also we add another sequence into the algorithm, which to control the distance. This algorithm, the ASMD3 algorithm, achieves optimal rate, and it is easy to implement in practice. And so we also conduct a numerical experiment on both simulated and real-world data sets to validate the convergence rate of the proposed algorithms. And here I will just give one example for the ridge regression. We will consider two settings for the constraint set and the corresponding distant generating functions. And in the first setting, the constraint set is a Euclidean ball. In this case, the distant generating function is chosen as 1/2 squared norm of x. And the second setting is the constraint set is a simplex on RD, and the distant generating function is the negative entropy. And as you can see on both figures, the accelerated algorithms performs significantly better than SMD. And for the new designed algorithms, ASMD and ASMD3, they both match the performance of the optimal rate of ASC-SA. Okay, the main takeaway of this work is summarized as follows. We propose the first continuous time SDE for ASMD with strongly convex functions, and we also designed several new algorithms for ASMD. Welcome to check our poster tonight at number 52. Thanks for attention.
Okay. Any question? Okay. Okay, so one question I have is that, so you're, in your proof of convergence for the right that you have, is it a proof that rely on the fact that you are using a discretization of a stochastic differential equation, or do you have to derive a more classical proof like Gadimi and Lan, which does not use any discretization or SDE?
In the proof of the SDE, actually, it's using the Lyapunov function to differentiate the energy function and to prove the convergence. And in the discrete time algorithms, actually, we also mimic the proof, and we construct a similar Lyapunov function as in the SDE, and the proof is kind of unified for this one.
Okay, thank you. So let us thank our speaker again. Okay, so our next speaker is Arman Kolarijani. He's going to talk about fast gradient-based methods with exponential rate, a hybrid control framework.
So let me add to the session share that it's a joint work with my supervisors, Peyman Mohajer Isfahani and Tamas Kevich. So basically, recently there's a renewed interest in using gradient-based optimization methods in optimal problems, and that basically has to do with nice properties of gradient-based methods, which they scale pretty nice. They're pretty easy to implement in practical settings, and also they're extendable to other settings such as non-smooth and non-convex cases. So that basically pushed the researchers to understand the intrinsic properties of gradient-based methods in a more comprehensive way. So one of the ways, basically, that has been there for a couple of centuries to understand gradient-based methods in a better way is basically using ordinary differential equations. So why is that? It's basically coming from the fact that when you push the step size towards 0, you recover some sort of differential equations. And then you can use tools from differential equations such as Lyapunov function to find some one-to-one relation between the continuous dynamics and also the discrete dynamics. Here in our study, basically we focus on basically a certain kind of fast gradient-based methods, which are called fast methods. For example, on the left side, you can see one of the most famous ones, which is Nesterov's fast method, which he proposed in 1983. Interestingly enough, these kind of techniques, they enjoy a higher order of convergence rate compared to the common gradient-based techniques. In a very nice paper in 2014 and in more completely in 2016, Sue, Boyd, and Candace find that when you push the step size for Nesterov's method towards 0, you recover a certain type of time-dependent second-order dynamical system. And that time-dependent variable is basically some sort of damping, time-dependent damping, which is equal to 3 over t. Another fact about fast methods in general is they have some sort of non-monotonic behavior, and you can easily relate it to the fact that they are damped second-order differential equations. And they, after time passes or the iteration number increases, you're gonna end up with some sort of oscillatory behavior in your basically optimal value or suboptimal equation. So how we usually researchers take care of that is via restarting schemes. And what is a restarting scheme? Basically, in the discrete case, you reset the y value to 0, and in the continuous case, you set the velocity value, which is x dot equal to 0. And again, you run the dynamics or the iterative algorithm, again. So the question basically we ask is, okay, you remember that gamma. We said, okay, why not be considered as a state-dependent variable, which depends on x and x dot. And now try to synthesize it using a control terminology or control techniques So maybe you can end up with some better properties in a general setting. So we shift from a time-varying system, which is a dynamical system, to a time-invariant system that is now a controlled system. So the main problem we address is basically as follows. Assume you have some sort of, as mentioned above there, unconstrained problem, and given some sort of a positive scalar, which is that alpha, we want to design certain type of dynamical system. We call that dynamical system hybrid control system, which I'll get back to later on. That the trajectories that hybrid system generates satisfy some sort of exponential convergence rate that is represented here. So what are the standing assumptions that we have is, one of them is basically your function should be twice differentiable, and the second one is it should have a bounded Hessian. And the other one is it should have some sort of gradient-dominated behavior. This is represented here. But the most important point in these assumptions is the second one and third one, they not necessarily require the convexity of your objective function. So now schematically, I can represent this slide what I was saying. So in the first one, which is the ordinary differential equations, which are damped, and we want to shift it to some sort of control problem and use feedback theory in order to design the damping term, which is state dependent. But we take it one step further, and we cast the problem as a hybrid control system. So why hybrid is important? Because hybrid system is basically a mixture of continuous flows and some discrete behavior, which we call it jump. And that discrete jump is basically equivalent to the restarting schemes that we were applying in the fast methods. So intrinsically, whatever we want to do with the algorithm, a hybrid form, which is represented on the left side in that calligraphic edge, it captures all the dynamics we want. So with this hybrid form, so what are the ingredients? So the first one is the flow map. Flow map is basically the continuous flow of your dynamics, which is basically the same as the second order, in the previous second order dynamics, but you replace the gamma t now with u of x, which is the input. What is the input? So we designed the input like this. I'm not going to go to the details of it, but later on I'll discuss what is the basic idea behind it. The input structure is as follows, and also the flow set. What is flow set? Basically, flow set is a partition of your state space that your hybrid system is allowed to evolve continuously. And as soon as it hits the boundaries of that flow set, the jump map appears again, which is represented here. And the point about the jump map here is basically what is distinguishing our approach from other people is basically here we consider some sort of a scale version of gradient, because usually in the literature the gradient would be the x2 would be reset to 0. So what are the parameters in that structure that has to be that have to be basically determined are u bar, u underbar, and beta. So based on that structure, our main result states that given that alpha, which is basically represent the convergence rate we want, if the hybrid control system I represented below has the parameters u bar, u underbar, and beta that satisfies these three kinds of inequality, then those generated trajectories are going to satisfy this kind of exponential convergence. So, okay, the math was there. Now, schematically, what does it mean? It's based on a type of quantity that we define, that sigma t. That sigma t basically partition the state space to 3 regions. And interestingly enough, you can see that basically your optimal solution belongs to sigma t equal to 0. If you basically put the optimal value over there in the sigma t in the above, you can see it belongs to sigma t equals 0. So our main point is, as long as you stay on the negative part of it, you can guarantee by construction that you have that type of exponential convergence. So the control, we synthesize the controller so it moves along certain level set in the negative side, and then we synthesize the jump map such that whenever you jump, you don't go over that sigma t equal to 0. And then step by step, you get closer to that sigma t equal to 0 and your optimal solution. And here I want to just explain briefly about the discretization. The discretization, because our input structure is state dependent, we face some difficulties, and it's a pretty tough job. But in order to have a discretization, to show that at least this continuous form has some sort of discrete representation, we change the flow set in a proper way. And also for the continuous flow, in order to make it discrete, we use the forward Euler method. And with certain type of parameterization, we can recover some results that is basically mentioned in the literature. Finally, here in this slide, you can basically see a comparison that we did with Nesterov-Fast method using Su et al.'s spurious starting scheme. Generally speaking, they have some sort of heuristic parameter, and in general, their approach, beat our approach because it has to do with the discretization we proposed. And so a proper way, a next step should be coming up with a better type of discretization. And for example, since our input is state dependent, a logical next step would be using some sort of geometric discretization instead of a simple forward Euler method. Thank you very much, and I would be happy to answer your questions now, and also if you have further questions after in the evening. Thanks.
So we have time for one very short question. Okay, so short question. So here, very often we analyze Nesterov's approach by using differential equations. Is there any hope to do that for second-order approaches like Newton method with cubic regularization?
Yeah, exactly. For Newton method, there are some kind of dynamical systems that can capture the properties,
including acceleration, like Nesterov's acceleration.
Yeah.
Okay, let us thank the speaker again. And welcome to the session Convex Optimization number 7. So you are the survivors of convex optimization. And we are pleased to welcome Peng-Tao Shi. And he's going to talk about diversity, promoting distance metric learning, convex relaxation, and theoretical analysis.
Hello, everyone. I'm Peng-Tao Xie from Phantom Inc. and Carnegie Mellon. I'm going to introduce our work, diversity promoting distance metric learning, convex relaxation, and theoretical analysis. This is joint work with Wei Wu, Yicheng Zhu, and Eric Xing. Distance metric learning is a widely studied problem in machine learning. The basic setup is as follows. Given data pairs that are labeled as similar or dissimilar, we learn a distance metric such that the similar data are grouped together and the dissimilar data pairs are separated apart. Typically, the distance metric is parameterized in the following way. We use a linear projection matrix A to project the data points x and y from the original feature space into a latent space, resulting in the latent representations A transpose X and A transpose Y. Then we calculate the squared Euclidean distance of A transpose X and A transpose Y. And this distance D is the distance metric we are going to learn. And the parameter matrix is A. The column vectors of A are called components, and each of them aims at capturing one latent pattern. A can be learned by solving this optimization problem, where for a similar data pair XY from the set S, we want to minimize their distance. And for a dissimilar pair from D, we are going to separate them with a margin 1. When applying distance metric learning, we encounter the following problems. The first one is that the learned distance metric performs less well on infrequent patterns compared with frequent patterns. The second problem is it generalizes less well on unseen data. The third one is it is difficult to simultaneously achieve both high retrieval precision and high efficiency. To address these three problems, we studied diversity promoting distance metric learning. The basic idea is to encourage the components in DML to be diverse. Why promoting diversity can address these aforementioned three problems? For the first one, better capture infrequent patterns. Here is an illustration, where we use the big circles to denote the frequent patterns and the small circles to denote the infrequent patterns. The components are denoted by the triangles. Since the frequent patterns are the dominant signals in the data set, DML tries to use a lot of components to ensure the frequent patterns are covered as best as possible. As a result, the infrequent patterns are ignored. By promoting diversity of the components, we can encourage the triangles to diversely spread out to different places in the space, and giving the infrequent patterns a better chance to be captured. Second, putting diversity over the model essentially imposes a structured constraint over the model class, which shrinks the functional class and reduces the risk of overfitting. For the third one, if we make the components mutually complementary, we can reduce the redundancy, and consequently, it is possible to use a small number of components to sufficiently cover the data, so that we can reduce the model size without sacrificing modeling power. There have been several regularizers proposed for promoting diversity, including determinant point process, decorrelation regularizer, mutual angular regularizer, uniform eigenvalue regularizer. The existing diversity promoting regularizers have two problems. The first one is they are non-convex, presenting great challenges for optimization. The second one is they are not amenable for theoretical analysis on two things: why promoting diversity can better capture infrequent patterns, and why it can improve generalization. So to address these two limitations, we make the following contributions in this work. This work is built upon our previous work published in last year, where we propose non-convex Bregman matrix divergence regularizers to promote diversity. On top of this work, we did two things in this work. The first one is to perform convex relaxation to turn the original non-convex regularizers into convex ones. The second part is the analysis. On top of the non-convex regularizers, we analyzed why promoting diversity can better capture the infrequent patterns. On the convex regularizers derived in this work, we analyze why promoting diversity can lead to better generalization. Specifically, we use near orthogonality to characterize diversity. A set of vectors are considered to be more diverse if they are close to being orthogonal. To encourage near orthogonality between two vectors, one way we can do is to encourage their inner product to be close to 0 and their L2 norm to be close to 1. Extending this to M vectors, we can compute the gram matrix between these vectors and encourage this matrix to be close to our identity matrix. On the diagonal of the gram matrix are the squared L2 norm of the vectors, and on the diagonal of the identity matrix are 1. Off the diagonal of this matrix G and I are the pairwise inner products and 0 respectively. So making G close to I effectively encourages the pairwise vectors to be close to orthogonal. We use Bregman matrix divergence to measure closeness of two matrices. Given a convex function phi, the BMD between two matrices X and Y is defined in this equation. Phi can be specialized to different choices, and under these choices, we have the specific instances of BMD, including the Newman divergence, log determinant divergence, and the squared Frobenius norm. We plug in the gram matrix G and identity matrix I into these divergences and get the corresponding regularizers, which are to be minimized to encourage orthogonality. Applying this regularizer to the distance metric learning problem, we have the BMD regularized DML problem. This problem is non-convex. To get a better local optimal, we need to restart the algorithms multiple times and pick the best solution, which incurs a lot of computational overhead. To address this issue, we perform convex relaxation to transform the original non-convex problem into a convex one. We first seek convex approximations of the non-convex BMD regularizers. By exploring the eigenvalues of A transpose A and AA transpose, we can get the approximations of these regularizers. Then within the approximation functions, we use trace norm of A transpose A to approximate its rank, which is M. And finally, we replace A transpose A with a semi-definite matrix M. Then we get these new regularizers, which are convex functions defined over this matrix M. Then based on this approximation, we can transform the original non-convex problem into a convex one, which is defined on this new matrix M. We use proximal gradient descent to address this, to solve this problem, which iteratively performs gradient descent and proximal operation until convergence. To derive the proximal operators, we need to solve the following problem, which is defined over M. And this problem can be transformed into D single variable problems that are defined over the eigenvalues of M. And each of these single variable problem can be solved in a closed form solution, which gives us these proximal operators. Next, I'm going to show some results in the analysis. The first one is about why promoting diversity can better capture infrequent patterns. So we first need to define a score to measure how well the infrequent patterns are captured. And this score is called imbalance factor. For each, we assume there are capital K classes in the data set. And for each class, we use the expectation mu to represent this class. Then we compute the pairwise distance between the classes, djk. And this imbalance factor is defined as a ratio between the largest interclass distance and the smallest interclass distance. Here is an illustration why this eta can characterize how well the infrequent patterns are captured. So on the left figure, we have two frequent classes denoted by the large circles, and two infrequent classes denoted by the small circles. For the two frequent classes, because they are the dominant signals in the data set, distance metric learning put a lot of attention on them and try to encourage their distance to be as large as possible. So we have a large D1. For the infrequent classes, because they are less prominent, so the model tends to ignore them, and we have a small distance D2. And consequently, D1 over D2, we have a large eta. By promoting diversity, we can give the infrequent classes, the two small circles, larger attention, and the distance metric learning model tries to make their distance to be large as well. And consequently, we reduce the value of eta. So the conclusion here is a smaller eta implies better capturing of the infrequent patterns. In this theorem, we show that it can be upper bounded by the increasing functions of the BMD regularizers. In the first part of this theorem, this bound is about this the Newman divergence regularizer, and in the second part, it is about the log determinant divergence regularizer. So that means if we reduce these regularizers, we can reduce the upper bound and leads to better capturing of the infrequent patterns. The second analysis is about estimation error. We analyze how the convex BMD regularizers help to reduce overfitting. In the function class, we assume the regularizers are upper bounded by a constant C. A smaller C entails stronger promotion of orthogonality, and C is controlled by the regularization parameter. In these estimation error bounds, we can show that the upper bounds are increasing functions of C. So this indicates that if we reduce C, which equivalently we promote more diversity, can reduce its upper bounds and leads to better generalization. We did the empirical study on 7 data sets, including electronic health records, text data sets, and image data sets, and sensor data set. In the experiments, two examples are labeled as similar if they have the same class and dissimilar if otherwise. The learned distance metrics are used for retrieval, whose performance is measured using AUC. Here is the training time achieved by different methods. The last panel shows our method, the convex Bregman matrix divergence regularizers. The second panel shows other diversity promoting regularizers, which are non-convex. Compare these two panels, we can see our convex methods takes much less time than the non-convex methods. This is not surprising because a convex method can achieve the global optimal in a single run, while the non-convex ones need to rerun multiple times to get a better local optima. In this table, we show the retrieval performance. The last panel are our methods. On the first 3 data sets, we divide the classes into frequent and infrequent. An infrequent class means it has more than 1,000 data examples. So the performance on the infrequent classes are AUC, RF. As can be seen, compared with the baseline, our method achieves better AUC on infrequent classes. On the overall performance, which is denoted by AUC all, our method are also better than the baselines. This indicates that by promoting diversity, our convex regularizers can better capture the infrequent patterns. This table shows the gap between the training AUC and the testing AUC, where our methods in the last panel outperform the baselines. This suggests that our methods are better capable of reducing overfitting. In this table, we show the number of projection vectors. Where can be seen on the last panel, our convex regularizers uses the smallest number of projection vectors to achieve the performance in this table. And combining these two results together, we can conclude that our regularizers can reduce the model size, which is proportional to the number of projection vectors, without sacrificing the modeling power. To conclude, in this work, we studied the convex relaxation and the theoretical analysis of diversity promoting distance metric learning. We transform the non-convex Bregman matrix divergence regularizers into the convex counterparts. In the experiments, we show that the convex regularizers are computationally more efficient and can better promote diversity because they are able to achieve the global optimal solution. We develop proximal gradient descent algorithm to solve the convex BMD regularized problems. On the analysis part, we first analyze why promoting diversity can better capture infrequent patterns on top of the non-convex BMD regularizers. In the second part, we analyze why promoting diversity can lead to better generalization on top of the convex regularizers. With that, I'd like to conclude here, and thanks for your attention.
Okay, we have time, yes.
Hello. So I have a curiosity, first of all. How did you select in your experiments this Bregman divergence regularization, and why? The reason why I'm asking is because I can see there is a kind of a mismatch.
Select what?
Between the way you enforced orthogonality in your metrics and the potential that you're using. It is only when this potential is sort of unitarily invariant that depends only on the on the spectrum, essentially, of the matrix, that the two things sort of match. Otherwise, I can see there's a geometric mismatch between the two objects.
Sorry, I didn't get the question. The mismatch between what two objects?
All right. The fact that you, okay, let me ask you the first question. Which regularizers did you happen to use in your experiments?
Which regularizers? The
Bregman divergence, matrix Bregman divergence.
So there are three instances. For each instance, we have a convex relaxation, and we did the experiments over all of them.
And sorry, I didn't get
including the von Neumann divergence, log determinant divergence, and the squared Frobenius norm.
All of them you use in your experiments?
Yeah.
Okay, I didn't see.
Okay.
We can take this offline.
Yes. Okay. Okay. So now our next speaker is Mathurin Macias. He's going to talk about a fast solver for the lasso with dual extrapolation.
Hi everyone. Thanks for staying so late. I'm Mathurin Macias from INRIA, and this is joint work with Alexandre Grandfort and Joseph Salmon. If you need a reason to stay focused for 10 more minutes at the end of the day, I'll give you this. At the end of the talk, you'll know how we went from 10,000 seconds to 50 seconds to solve the lasso cross-validation pass on a dataset with 1.5 million features. And small spoiler, the two key ingredients are extrapolation in the dual and a fast-working set algorithm. So I'll remind the popular lasso estimator. It is defined as the solution of the following optimization problem, where we have a design matrix X with n samples and p features, a vector of observation Y in Rn. And the lasso is popular because the solution beta hat is going to be sparse, meaning that it has few non-zero coefficients compared to its dimension p. What we also will need is a dual problem of the lasso. So right now we are maximizing a simple function. If you look at it long enough, it's a concave isotropic parabola. But we maximize it over a complex set, delta of x, which is called the dual polytope in the case of the lasso. And here is a small examples with 2 sample and 3 features. So the dual is in dimension 2. And you see that each feature defines a slab, which are the light gray zones, and the intersection of these slabs is delta x. One of the problems of the lasso is that as an optimization problem, there is no closed form formula. But the primal objective function has a nice formulation in the sense that it is a smooth plus separable problem. So an algorithm which works extremely well is coordinate descent, meaning that we are going to take the primal objective function p of beta as a function of each of the coordinates of beta and minimize it with respect to beta 1, then beta 2, up to beta p. This is what we call an epoch. And we cycle again. And as you can see, cyclic coordinate descent is an iterative algorithm. We will never reach the exact solution, so we need a stopping criterion. This is where duality comes into play for the first time. We have a nice result which says that for any primal dual pair beta theta, the primal objective at beta is larger than the dual objective at theta. So the quantity that we are really interested in is this guy, the difference, p of beta minus p of beta hat, but we do not know beta hat. What this tells us is that if we construct a dual point theta, then the duality gap p of beta minus d of theta will be an upper bound of the quantity that we want to control. So now the question becomes, which theta do we pick? And the canonical approach is called residual rescaling. It is inspired from this equation, which holds at optimum. It's derived from the KKT condition. And it tells you that the solution of the dual is equal to the residuals, y minus x beta hat, divided by lambda. So if you are not at optimum, if you do not have beta hat, but you have some beta t at coordinate descent epoch number t, you compute the residuals y minus x beta t, and you divide them by lambda. But if you do this, you do not have the guarantees that the point you constructed is in delta x. So what people do is to divide it by a constant large enough so that it shrinks and goes back to delta x, hence the name residual rescaling. It has some advantages. First of all, it's simple. It converges to theta hat if your algorithm converges in the primal. And it's not so expensive to compute. The main cost is this guy, which is O of NP. This is the same as one epoch of coordinate descent. So of course, you will not compute it at every coordinate descent update. You do maybe 10 epochs of coordinate descent, and then you compute your stopping criterion. But if you think about it, it also has some drawbacks, residual rescaling. And the first one is that in some sense it's imbalanced because you do all of the efforts in the primal, and then for the dual you just do a brutal rescaling. So as you can see here on this simple experiment, the quantity that we are really interested into is the green curve, and the upper bound, which is constructed with the canonical approach, is in blue. You see that there's room for improvement. One of the reasons there's room for improvement is that residual rescaling ignores every information about the past. So you may be at iteration 1000 of coordinate descent, and you just throw everything away, you take your current residuals, and you rescale them. So this is where we try to improve the construction. And the idea is based on extrapolation. If I give you this sequence, and I ask you for the limit, and the best guess you can tell is 1. What did you do? There was structure in the sequence, and you extrapolated. So as we will see, there is also some structure in the sequence of residuals. And we are going to use the same idea to infer the limit of the residuals, which, as we know, converge to lambda theta hat. So we will get another dual point construction. This is a slide I do not want you to read. It's just we are going to keep past of the k-pest residuals. We solve a k by k linear system. We get some coefficients out of it, and we are going to use an affine combination of the past residuals to extrapolate the residuals. This point is not necessarily feasible, so we rescale it also. But the important thing in this slide is that we will pick k equal to 5. So it's cheap. You just keep 5 residuals, you solve a 5 by 5 linear system, and you get an alternate dual point construction. The reason why it works is because there's structure in the residuals. In the sequence I gave you, there was some structure here. Once the support is identified, so I'll refer to the talk of Clarice Poon earlier, then beta t and the residual, for example, for ISTA, it's very easy to see that they follow what is called a vector autoregressive process, even without noise, so it's very regular. And then extrapolation will kick in. The same, we have reasons to believe that the same holds for coordinate descent, even though it's a bit more tricky to compute. No, to show, sorry. But still, you could have lots of bad things happen before you identify the support. But remember that our approach is very cheap. So we can still use the canonical approach, and we just pick the best of the both. And in practice, you see which one is best. So in green, this is ours. And you see that in the beginning, it does not behave hierarchically. It behaves like the blue one, the classical one. And then here, it really extrapolates because the residuals start to have a structure. This corresponds to support identification. And in the end, you get a much tighter estimate of suboptimality. So this is the first gain, but there's more. In practice, vanilla coordinate descent is seldom used for the lasso because you know that your support is going to be small. So if you could ignore the coefficients which are 0, then the size of the problem decreases and it becomes easier. So the first approach, which are called screening rules, and it's a backward approach. You start with every features, and periodically you compute some tests for each feature j, and if the feature j satisfies this inequality, then you have the guarantee that at optimum beta j is 0. And as you can see, this test, this is gap-safe screening rule, so it's state-of-the-art for screening rule. This test, it depends on the dual point theta and of the gap. So if you have a tighter gap, it's easier to satisfy this inequality. This is what we show. This is the data set I was talking about. It's a finance one with 1.5 million features. You see that with our approach, as we get a gap which decreases to 0 faster, even though nothing changes in the primal, we are able to remove more variables earlier. And there's a complementary approach to screening, which is called working sets. It's a forward approach. You focus on some coordinate, you solve the problem restricted to it, etc., and you iterate. State of the art for this is Blitz. To be fair, Blitz addresses more problems than we do. Currently, we only do the lasso, but we are able to beat Blitz on a lasso cross-validation path. And if you want to reproduce all of these figures and play with the code, it's an open source package online. Something which is cool is that it has the same API as scikit-learn, so if you have some code which uses sklearn lasso, you just import it from Celer instead. The name of the package is Celer. It means constraint elimination for the lasso with extrapolated residuals. And before you leave, this is the take-home message, that if you use residual extrapolation, you can be as fast as my boy. And I hope to see you at poster 117.
Any question?
So for the dual extrapolation, how many iterates did you need to use? Did you use all previous iterates? 5.
It's one. It's so cheap in memory. It's like you had 5 features.
And study the influence of this parameter. Let's say if you use 100, does it make a difference, or?
If I use more?
Yes, or less?
5 is already good. We have a figure in the appendix of the paper. It's a trade-off because you need to use at least a few to get the structure. And if you want to use too many, then first the cost blows up because you have O of k squared, cube to solve the system. Also, you need to wait because in the beginning, when you accumulate the residual, you cannot use extrapolation. So k equal to 5 is great.
Okay. Let us thank Mathieu again. And so we are pleased to have now Hugo Raguet, who is going to talk about cut pursuit algorithms for regularizing non-smooth functionals with graph total variation.
Okay, thank you. So I'm Hugo Raguet, and this is a joint work with my colleague Loïc Landrieux. And just like the previous talk, I'm going to talk about the tremendous acceleration of a very popular convex optimization problem. So this one is not the lasso, but involves the graph total variation. And we'll show how to apply the cut pursuit algorithm in the presence of other non-differentiable parts. So we are dealing with the main functional capital F here, which is structured over an arbitrary graph. It involves the graph total variation, which is basically the sum over finite differences of neighboring vertices weighted by some weights. And we'll also allow an arbitrary part, which is differentiable, and a possibly non-differentiable part, but we'll ask for now to be separable with respect to the vertices of the graph. So each JV here is a real functional, possibly taking values plus infinity. So this kind of structured optimization problem, we already have many iterative algorithms to solve them. But most of them, I mean all of them actually have the drawback that they tend to visit each vertex independently. Whereas the graph total variation is specifically here to enforce solutions which are piecewise constant over the graph. So basically, there will be a partition of the vertices over which each partition is going to be constant. So the idea to use this is introduced by my colleague, is to use a working set or active set strategy. Basically, we'll maintain a list of the edges which will be allowed to have non-zero finite differences, and so equivalently maintaining the partition of the graph into constant connected components. So how does that work exactly? So this script V here is a partition of our set of vertices, and we'll look for minimizers which are constant over each of the components of this partition. And how does this the main functional restricted to this condition looks like? It has this following form. The graph total variation here, the finite differences within each component vanishes, while the finite differences in between components are now weighted by the sum of the weights of the edges linking the components. we can also observe that the smooth part, in terms of the values of the components, is still a smooth functional, whereas the non-differentiable part, in terms of the values of the components, is also separable, but not along the vertices of the graph, but now along the components of the partition. So altogether, we observe that this reduced functional is exactly the same structure as the main functional, but on a much reduced graph, where the vertices are now the constant connected components of our partition. So on that much reduced graph, using our iterative algorithms will be much, much faster. So this gives rise to the natural idea of the cut process general scheme, which would be to start with a very coarse component. Let's say here in the illustration, we start with only one component, which comprises all vertices. And so we solve the reduced graph. We search just for one scalar. And then somehow we have to activate some edges and refine the partition accordingly and the reduced graph, solve it again, refine some more, activate some more edges, then refine, solve again the reduced problem, and terminate the algorithm when no further refinement can be found. So this general cut process algorithm actually can be applied in a more general setting than what you are considering here, as long as we have like graph regularity inducing penalization. But for our setting, so we've seen already how to solve the reduced problem. It's pretty easy. And we'll see now how do we refine the partition. So to do that, we'll use actually first order information. So in addition to separability, we'll also ask the functional G to be directionally differentiable. So this is an illustration of what could one real functional GV look like. You can note that we also allow for infinite directional derivative. So the directional derivative of our main functional given our current iterate x and a certain direction d looks like this. So here are some unary terms in terms of individual directions of the coordinate of the directions, and here are a coupling binary terms that comes from the graph total variation. And what we would like to do is find a steep descent direction, and using the constant connected components of these steep descent directions to activate the edge or update the partition. So to make a long story short, a good search space for this steep descent direction would be to ask for descent directions which either at each vertex either increase the value, decrease the value, or stay at the same value. So why is it a good search direction? First of all, it's a finite set, and we see that we are facing now a combinatorial problem. And this we can actually show that this is equivalent to, finding the steepest direction here is equivalent to finding a minimum cut maximum flow problem in a conveniently designed flow graph. So we can call on a very powerful algorithm to do that in a small amount of time. So, and a second reason why it is a good search direction is that actually, as long as x, our current iterate, is not a stationary point for the main functional, we are ensured that there will exist at least one strict descent direction in this set. So altogether, as long as there is strict descent directions, we know that this set is rich enough so that at least one of the strict descent directions will be in it. And in the long run, we can show that this will ensure convergence of our algorithm toward the stationary point of the main functional. A quick word on the fact that we can go beyond strict separability. So this is a multidimensional case where each value at each vertex is now multidimensional in R to the k. The main difference is that here the absolute value is replaced by some kind of norm in the graph total variation, and the JV here are now multidimensional. So this is a multidimensional version of my JV, monodimensional JV. And one can directly see that the main problem is that now a direction in the space Rk is not summed up by either decreasing or increasing direction, but we have actually an infinity of possible directions. But to still get a combinatorial problem for the descent direction, the natural idea would be simply to choose smartly a finite number of possible candidate directions, which could evidently depend on the vertex, on each vertex, and also on the current iterates of our minimization. So altogether, the directional derivative of our problem would look like that, and our combinatorial problem here is now a multi-level one, which in contrast to previously cannot be solved with only one graph cut, but we still can call on alpha expansion algorithms or on the likes to solve it approximately using a series of graph cuts. So, now let's see how useful is that. My first numerical experiment is a middle scale. This is inspired from brain source identification problem. This is actually a linear inverse problem where we would like to enforce sparsity and positivity over the coefficients, as well as spatial regularity over the mesh defining the graph of our model. And so here is the evolution of the functional along running time. So these are, let's say, state-of-the-art proximal splitting algorithm. Please come back to me. Yeah, perfect. Okay. And so these are state-of-the-art proximal splitting algorithm, and here is like real time. It's actually 0.2 seconds, so that represents 2 orders of magnitudes of acceleration, and this could be explained by the 1,000-fold difference between the number of final connected components of our problem and the number of vertices in the original graph. Very quickly, another numerical experiment involving multidimensional data. This is so regularization of classification of 3D point clouds. So each we are given a point-wise classification of each point belonging to a certain class, and we'd like to regularize it using graph total variation. And here are the results. Note that we can solve the problem with only 4 cut process iteration, but in this case, the data are multidimensional, so each cut process iterations will ask for much more graph cuts in the huge original graph. So that's why we are still able to gain an order of magnitude over proximal splitting algorithm. So very quick conclusion. So we're actually achieving tremendous accelerations. And so I'd like to mention that the same scheme can be applied in the presence of non-convexity, nothing presented. There are some codes readily available online, and better is to come, because one observes that it's possible actually to perform the refinement step independently over each component of the current partition. So actually this is an opportunity to parallelize it, either to accelerate even further the algorithm, or maybe we can also imagine distributed memory architecture where we can actually solve the main problem without never having to look at the entire graph. So thanks for your attention.
Maybe a very, very short questions to stay on schedule while Dimitri is setting up his computer. Okay, very short question about the fact that the problem you consider, if I'm correct, the solution is not unique. So is it a problem? Can you say one quick word about it?
Actually, so yeah, in that context, it's usual that the solution is not unique, and I'm using this opportunity of your question to precise that with the total variation along the possible solutions, we know that some are presenting staircasing effects, and the cut processing algorithm, since it's seeking for a partition with a minimal number of connected components at the end, usually we are avoiding solutions with staircasing effects. So basically, if we have several solutions, we tend to use the best one.
Okay, thank you. So let us thank Hugo again. And now Dimitri Ostrovsky is going to present his work about efficient first-order algorithms for adaptive signal denoising.
Okay, so let's start. Okay, so first let me present the problem. So we're interested in discrete time signal denoising, means to denoise a signal called X with discrete time index tau. The signal is possibly complex valued, and it's given, well, it's observed in the white noise, in the ID Gaussian noise scaled by intensity parameter sigma. So the goal is to infer it from these observations on a finite horizon n. And whereas you can see that our assumptions about the noise are completely standard, what is non-standard here is the structure of the signal. So as opposed to what is usually assumed in the classical estimation setups, be it non-parametric or parametric statistics, the structure of the signal here is not known in advance in the statisticians. Think, for example, about estimation of a smooth curve. Okay, so when there is a smooth curve behind this x, then in this case, the curve is something which is, smooth curve is something which is close to a particular subspace of small degree polynomials, and this subspace space is known to the statistician in advance. So here we avoid such strong assumptions, and the way to do this is by using the adaptive signal denoising framework developed and studied by my co-authors and myself before in the previous papers. So a brief glimpse into this framework. We start with defining linear time invariant estimators. Each such estimator is simply a discrete convolution with a filter phi. So the filter is given on the on the left half, let's say, of the subdomain of the length n. That allows us to obtain an estimate on the right subdomain. Then we can switch the subdomains and obtain the whole estimate. Okay, so the time invariance of this estimator is captured by the fact that the filter phi is kept constant when we change the time index t, okay, of the estimation. And the main oracle result which motivates this definition is the following. So suppose that x is in some sense regular, but its structure is unknown. Okay, this is formalized by the fact that x satisfies some unknown ordinary difference equation. Okay, so delta is the lag operator, and for some polynomial of small degree, this polynomial can be unknown, p of delta is approximately 0. Then it turns out that there exists a filter, a linear time invariant estimator with good statistical properties. In particular, there exists a filter phi O, the oracle, such that its estimation risk with respect to different notions of the loss is near minimax, and also it has small L1 norm in the Fourier domain. And this structural property is especially helpful. Okay? So given the existence of this good oracle, the goal of the adaptive theory is to find an adaptive filter phi hat, which can be constructed from the data y, hopefully in an efficient manner, and has similar statistical properties to those of the oracle estimator. Well, long story short, this goal has been achieved previously. And the way to do this is the following recovery procedure. So you minimize the residual, the Fourier domain residual, which is LP norm of the discrete Fourier transform of your recovery error, so basically of the discrepancy between the observations y and their convolution with the filter. So in other words, we're trying to find a filter which reproduces the observations with natural L1 constraint in the Fourier domain. And in particular, there were studied two versions of this procedure with L2 fit called least squares, okay, constrained least squares, and the L infinity fit called the uniform fit procedure. They are slightly different. They have different statistical guarantees. So one is better suited for the L2 loss, another one for the pointwise loss guarantees. Now, in this work, what we're interested in is the algorithmic questions. So basically, implementation questions. First of all, how do we compute the solutions of this optimization problem efficiently? And second, is it true that low accuracy solutions are actually, crude approximate solutions are actually sufficient? Okay, because we are not interested in solving this problem per se, we're actually interested in taking its solution or approximate solution as a statistical estimator, okay, as a proxy to the oracle filter. It turns out that for a number of reasons, first-order methods are natural in this connection. So first of all, the constraint set has a simple structure, it's proximal friendly. We have first-order oracles which are readily available, and they're reduced to convolution, so they can be computed by f of t and log n. And also we studied this low accuracy question in detail, and first-order methods are naturally suited to obtain crude solutions of optimization problems. Okay, so what are our strategies? So for the least squares problem, we approach it by, well, first of all, we pass the variables, we pass to the Fourier domain. So we introduce the variable u, which is the Fourier transform of the filter, and the corresponding linear operator a, which can be efficiently computed because it's amounts to the Fourier transform of a non-circular convolution. Okay. So somehow it can be reduced to f of t. Now, with this change of variables, the least squares problem becomes a quadratic problem on the L1 ball. And for such problems, we can address them using a version of the generalization of the Nesterov algorithm, fast gradient method with 1/t² convergence. And the uniform fit problem can be restated as a bilinear saddle point problem. So this kind of problems can be naturally solved by the mirror-prox algorithm with 1/t convergence after 2 iterations. Now, both of these strategies have very good properties. So first of all, both algorithms allow for L1 suited geometry for L1 proximal setups. We also can equip the two algorithms with dual certificates, which allow to control the accuracy after, well, for early stopping upon reaching the desired accuracy. Then the adaptive step size, we can employ this technique as well. And also, if we would like to consider penalized versions of the problems, there are proximal versions of the algorithms. Now, our first theoretical result concerns the what we call statistical accuracy, epsilon star. So basically, statistical accuracy is the accuracy of solving the optimization problem in the objective such that the guaranteed, related approximate solution has similar statistical guarantees for the actual loss as the exact solution. So it turns out that, I won't go into detail, so basically the least squares estimate allows, from the previous work we know that it allows a good high probability guarantee on the, for the L2 loss, and for the uniform fit estimator, similar guarantee holds for the sup loss. So basically, we prove that upon reaching accuracies which scales as sigma r for the uniform fit estimate and the square of this quantity for the least squares estimate, we have similar guarantees for the corresponding approximate solutions. Now, this result can be used in a nice way. So what we can do is that we can simply use the dual certificates to reach this accuracy epsilon star and then look at the quality, statistical quality of this estimate. So in particular, in this experiment, we compare two estimates. One is the crude solution. So, okay, so the setting is as follows. So this is a synthetic data scenario. What we do is that we generate random sinusoids, a sum of 4 random sinusoids with arbitrary frequencies. Now, we do this many times. And we also consider a slightly different framework where the frequencies are coherent. So the frequencies are close and the sinusoids are grouped by pairs. So now what we compare are two algorithms, two estimators. One is the crude solution of least squares with prescribed accuracy from the theorem. And another one is the solution of least squares with 100 times better accuracy. So surprisingly, what happens is that, well, first of all, unsurprisingly, the time to compute the two estimators differs by an order of magnitude, right? What is surprising is that the L2 error is virtually the same for the two estimators. We also compare them with the lasso estimator. And I won't go into details here. We can discuss this offline, I guess, or at the poster. Now, second small result, a small addition, is that since we know how to control this accuracy, we also can obtain the number of iterations sufficient to reach it. This iteration, T star, turns out to scale in this nice way as peak SNR in the Fourier domain, okay, at most up to some constant, if the correct algorithm is used to solve the problem. So for the uniform fit, this is mirror prox, and for the least squares problem, it's the fast gradient method. So we also evaluate this this result empirically in a similar synthetic data scenario. Thank you very much. See you at my poster. It's number 51, hole B. And also there is a small addition. I will show you how to solve a certain non-smooth problem in 1 over t squared. Thank you.
Okay, so maybe a very short question while the next speaker sets up his laptop. Okay, so there is a natural, very short question. What about this last sentence about the 1 over t squared? Oh, do you have a smaller hint about what you meant by certain non-smooth problems with?
Well, I can actually just sound it right now. So basically, if you solve a problem which is minimization of the L2 norm of AX minus B, where X is constrained to be in some set such that there is no exact fit, so that the optimal value is non-zero, then you can solve instead. Well, it's another question why you would be interested in solving this particular problem, why you would be interested in measuring the L2 norm fit that you might be for some statistical reason. But the surprising fact is that by solving the squared problem instead, right, it's equivalent to the squared problem with squared residual, you can solve it by necessary of obtaining 1 over t squared convergence. Now what happens is that simply using the difference of square, if you know that the optimal value is non-zero, so the fit is not exact, you can just divide by it and get the similar rate for the norm minimization. So this might have some implications. I'm thinking about it.
Okay, thank you. So let us thank Dimitri again. And our last speaker of the day is Li Shen. He's going to talk about an algorithmic framework of variable metric over relaxed hybrid proximal extra-gradient method.
Hello, everyone. I'm Li Shen from Tencent AI Lab channel. My work is titled as an algorithm framework of variable metric over relaxed hybrid proximal extra-gradient method. This work is joined with Peng Sun, Yitong, Wei Liu, and Tong Zhang from Tencent AI Lab. In this work, we focus on the monotone operator inclusion problem. This problem looks very simple, but is actually an extension of the KKT generalized equations for non-smooth convex optimization and convex concave set point optimization. It also covers a variety of applications in statistics, machine learning, and so on. Here, T is a maximal monotone operator, and X is a finite dimensional linear vector space. Moreover, we assume that the zero solution set T minus 1, 0 is non-empty. One of the most efficient algorithms for monotone operator inclusion problem is the proximal point algorithm. Here we call it PPA, and its over-relaxed variant. Here GSA T is the resolvement operator of T, and theta is the over-relaxed step size for acceleration. The main drawback of the relaxed PPA is that the resolvement operator GSAT may be difficult to be solved. To tackle this difficulty, an exact PPA is proposed. Its convergence rate is guaranteed if the absolute error condition or the relative error condition holds. However, it's too flexible to preset the hyperparameter psi k, which highly influence the level of computational cost and the quality of iteration. Later on, two types of new inexact PPA called hybrid proximal extra gradient algorithm. Here we call it HPE algorithm, are put forward. The two methods use a new relative error condition. The original HPE algorithm do not use the over-relaxed step size to accelerate the algorithm, and the extra gradient step size in the second algorithm has to be adaptively determined to ensure its global convergence, which requires extra computation and may be time-consuming. In this paper, we propose a new variable metric over relaxed HPE algorithm called VMOR HPE algorithm to solve the monotone operator inclusion problem. This algorithm generates the iteration sequence in terms of a new relative error condition and introduce an over-relaxed step size in the extra gradient step to improve its performance. In particular, the extra gradient step size theta k can be set as a fixed constant in advance, which saves extra computation. Moreover, the operator mk is introduced to explore the curvature information of the maximal monotone operator T. Here, we emphasize that theta k breaks the ceiling of the over-relaxed step size theta belongs to the region -1 to 1 in the literature. Moreover, in our work, we show that VMOR HPE algorithm is a powerful algorithm framework that can cover a class of first-order primal and prime-dual splitting algorithm as a special case. For the prime algorithm, it covers forward-backward splitting, Douglas-Richard splitting, proximal gradient algorithm, and generalized forward-backward splitting, and so on, as a special case. For the prime-dual splitting algorithm, it covers conduct-Yu prime-dual splitting algorithm and a new generated proximal ADMM EBB algorithm as a special case. Below, we will give a deep look on a few instances. First, we consider the three-operator inclusion problem. Here, A is a maximal monotone operator. B1 is a bait concursive operator, and B2 is a monotone and elliptical continuous operator. Very recently, a forward-backward, half-forward algorithm is put forward as this formulation. It should be emphasized that this algorithm covers forward-backward and forward splitting algorithm as a special case. Interestingly, we can show that this algorithm falls into the framework of VMOR-HPE. In addition, we also show that the non-self-adjoint metric FB-HF algorithm also falls into our framework of VMOR-HPE algorithm. In the non-self-adjoint metric FB-HF algorithm, P is a block triangle linear operator. The resolvement of A can be calculated in the Gauss-Seidel style sequential computation. Next, we consider the finite sum structured optimization problem. Here, Gi and R are proper closed convex functions which may be non-smooth. A new distributed splitting algorithm called proximal gradient algorithm is proposed to solve this problem. Here we define a composite operator, S alpha, and the gradient of S plus subgradient of G. We can check that this operator is actually a maximum monotone operator if Fi, Gi, and R are convex functions. By using these notations, we can show that the PPG algorithm also falls into the framework of VMOR-HPE. Next, we consider the three-term composite optimization problem with a coupled linear operator B. Here, F is a smooth convex function. G and H are simple convex functions. Using the optimality condition, the three-term optimization problem can be formulated as the maximum monotone operator inclusion problem. One of the most popular first-order prime-dual algorithm to solve this inclusion problem is the conduct-Yu prime-dual splitting algorithm. It takes the following formulations. By denoting a linear operator M, we can show that the conduct-Yu prime-dual splitting algorithm is covered by our framework. Recently, a symmetric forward-backward adjoint splitting prime-dual algorithm is also covered by our VMOR-HPE framework. At last, we apply our new framework to solve the linear equality constraint optimization problem. Here, AI is a bounded linear operator, Gi is a proper closed convex function, and F is a smooth function. By introducing the Lagrangian multipliers Y, the KKT generalized equation of this constraint problem is defined as this form. Now we can apply the VMOR-HPE algorithm to solve this inclusion problem. Then we obtain the following PADMM EBB algorithm. This algorithm is new. In the implementation, it first generates the VK epsilon K satisfying the relative condition via the proximal ADMM. Then it performs an extra gradient step to ensure the global convergence. Moreover, the metric M is generated via the BB9 search technique to explore the curvature information of the KKT mapping. Since that PADMM EBB is a special case of VMOR-HPE algorithm, its global convergence, iteration complexities, and local linear convergence rate are directly derived. In our work, we propose a novel algorithm framework of variable metric over relaxed hybrid proximal method and establish its global convergence rate, and iteration complexities. In addition, this framework covers a large class of primal and prime-dual algorithm as a special case and serves as a powerful analysis technique for characterizing their convergence and the convergence rate. At last, we apply the VMORHP framework to linearly equally constrained optimization problem, yielding a new convergent prime dual algorithm. Here we do not present the numerical performance, and there are many details on how to cast the existing primal and prime dual algorithm to our VMORHP framework. Please come to our poster for the details. The poster will be ready 10 minutes later.
Okay, any question for the last talk? So very short question about the variable metric aspect. I didn't really get how you chose the different metrics.
Yes, different metrics M will yield a different first-order algorithm.
So how are these metrics obtained? How they are obtained, these metrics? How did you choose them?
For the PADMM EBB algorithm, the metric M is defined as this form. For the PPG, for the proximal gradient algorithm, the metric M is identity matrix, but the maximum monotone operator S is very complicated. Here, but we can check that this operator is a maximum monotone operator.
Okay, let us thank our speaker again. And so that will conclude this session.